All right, so welcome to our first environment for 322, and it's going to be the Earth environment, so soils. So this particular lecture is going to focus on characteristics of soils and some terminology that's going to be important to us. If you've taken a geotechnical engineering course or a water resources course, some of this is going to be familiar, but if you haven't, don't worry, we're going to get through enough background information that it'll start to link the concepts together. So soil is what we call Earth's living skin. It's the thin veneer of material that covers much of the Earth's surfaces. It's frequently less than a meter thick, but it's absolutely vital for human life. The complexity of soils are driven by two things that are going to matter to us as environmental engineers and that matter to anybody who studies soil. The first is the abiotic soil structure. So biotic means living. Remember, if you put an A or an AN in front of a word, it means not. So the not living components. The biotic components, the diversity of the living organisms in soil is going to be really, really important and drives a lot of the complexity. So a lot of the biotic diversity that we see in soils is driven actually by a large amount of energy from the sun and photosynthesis. We have a lot of organisms that sit right at the top layer of soils that are going to be important, that have the ability to do photosynthesis. But as we go down through the layers, we're going to see metabolism change, mostly moving to chemoheterotrophic. So two components when we talk about complexity of soil, we have abiotic, which is the non-living, and the biotic, which is going to be our microorganisms. The abiotic component of soil is going to be really important structurally to what's happening with the living organisms. So inorganic particles within the soil are going to differ in size, shape, and what we call morphology. So think of morphology as kind of characteristics related to what the particular component is. So having those different size, shapes, and morphology is going to result in different surface areas. And surface area is always super, super critical because it impacts soil chemistry, the rates of reactions, and how many microorganisms can cling to different surfaces. So soil structure is going to help to regulate water movement and retention within the soil, gas exchange within the soil, and any potential sites where we could have redox reactions occurring. So what you're going to see on the right side of this screen is a soil aggregate particle. Let me grab my laser pointer. So these components here on the soil particles are called aggregates. The spaces in between, we call an intra-aggregate pore space, so between aggregates. And then within an aggregate, that's an inter-aggregate pore space. So if they're between aggregates, they are intra-aggregate pore spaces. If they're within the aggregate itself, they're inter-aggregate pore spaces. And the reason that we care about that is that water is going to move through soil, and gases are going to move through soil, and those spaces in between things are going to matter to us quite a bit. So that's kind of the overview of what's going on abiotically. And then the biotic component is going to consist of a lot of different things. So first, it's going to consist of decaying residues, what we call soil humus, which is that really dark, earthy kind of material, plant vegetation, and soil organisms. So normally when we have nutrients that are being released in a soil environment, they are because of microbes decaying those different components within the soil. So that's important. The fact that soils are what we call very heterogeneous, that means they're very different across different spectra of the earth, is going to allow aerobic and anaerobic organisms to exist in close proximity to each other. So on the last slide, when we had those aggregates, the spaces in between the aggregates allow for gas exchange. So it allows for oxygen, but then we can also have organisms shielded from oxygen in more compact soils, and we could then have more of an anaerobic environment. So we're going to see the ability to have those organisms in very close proximity, and that's great because we want a diversity of organisms. Autotrophs in soil are also going to be really important for biogeochemical cycling. So they're going to be really important about pulling nitrogen phosphorus, and sulfates into chemical reactions. So cycling of those three components are really, really critical to the Earth's natural balance. And there are biogeochemical cycles associated with nitrogen, phosphorus, and sulfate. The last component related to the biotic component is that they're very prolific organisms. So we end up with very diverse communities in a very small space. You've heard me say in class already that if you pick up a soil sample, you get a lot of microorganisms. Well, here's finally the number that you've been waiting for. The estimate range is 2,000 to 8.3 million different species per gram of soil. Gram is the size of a paperclip. It's very, very, very diverse, and that's really important. So one of the things that we're going to make sure that we talk about is that there are different zones within soil that matter to us. So we have surface soil at the very top. Let me grab my laser pointer. There it is. That is an unsaturated area. Then as we move down, we enter what's called the vadose zone, which is an unsaturated area where there's no spontaneous water movement. Then we hit a region called the capillary fringe, where the water table is starting to interact with that vadose zone, and it's almost a saturated environment. Then we hit the water table and we hit the saturated zone, where there is spontaneous water movement. So these different layers are not only about depth, but they're about how much water is there. And the saturated zone for us, it could either be a groundwater aquifer or it could be wetlands, and both are relevant to us as environmental engineers. So the other thing that I want to make sure that we hit before we talk too much about those different zones is how soil is actually formed. So soil forms, it doesn't just spring into being, right? It forms as a result of many different factors. So here are the 5 big ones that we care about. The first is the parent material. So this is whatever the rock or the mineral base from that soil is formed, and that rock gets weathered and eroded over time. And as it erodes, those different components of the rock end up as part of the soil. So we call that the parent material. Then we can have the climate. So precipitation and temperature are really, really important, because think about wind moving across rock or water moving across rock. It's going to cause that erosion and that weathering. So climatic factors and how much rain is occurring or what the temperature fluctuations are going to basically determine the rate at which that weathering happens. Then organisms are also going to be an important component of what type of soil we get. So things like plants, animals, microbes are going to add organic components. So the parent material is mostly inorganics. But the plants, animals, and microbes add that organic matter, and that's going to aid in the process of decomposition and nutrient cycling. And it's going to help with that weathering process as well. Topography is going to matter, so particular site slope, angle, and length. So what is exposed to weather and what is not exposed to weather. So a really good example of this is the Appalachian Mountains versus like southern Utah in the southwest of the United States. Completely different parent materials, completely different weathering patterns, and completely different climates. So the soils there are very different. And then the last is going to be time. So it takes time for things to weather out. In general, soils that form more rapidly are going to form in warm environments compared to cold ones. So, quick question, where would we expect to see more microbes? In that surface soil or the subsurface? Take a pause and think about this. So the answer is going to be the surface, and the reason why is because surface soil has much more vegetative decay and biotic inputs. The subsurface is not generally weathered by the climate. So normally weathering is occurring at the very, very top, and we have more vegetation at the top. So there's more diversity in terms of what's actually there for microbes to live with in that surface layer. So we're mostly looking at the surface layer for this class. So just to kind of show you that that is true, this is going to show you the different layers and the direct counts of microorganisms. So you can see that the amount of microorganisms goes down as you go further into the subsurface. It's not that they're not there, they are there. But then if we look at what's called viable counts over here, these are alive bacteria. You can see we're orders of magnitude, 5 orders of magnitude, or about 4, greater than what we start to see in the subsurface. So we're not necessarily seeing the culturable or the viable organisms here, viable meaning alive. But when we look at the viable counts, then we're seeing that bigger diversity and more viable organisms up in that top layer. So I just want to make some notes really quick on some of these different zones because they do matter to us as environmental engineers. So if you haven't heard of it before in other classes, the vadose zone is a subsurface zone and it's unsaturated and it's considered an oligotrophic environment, and it's between the surface soil and the saturated zone. So it's going to consist mostly of unweathered parent material because it's not exposed to the elements, and low organic carbon content, which is part of what's going to limit microorganisms. The thickness of it is highly variable depending upon where you are in the world, but the huge relevance to us is that microbes can pass from the surface and be filtered into the vadose zone before reaching a groundwater well, because the groundwater well is going to be below the vadose zone. So the vadose zone itself is going to act like a massive filter as organisms move down and water moves down through soil. And so this zone in particular is actually how we've come up with drinking water filters. It's part of the reason that we think about using sand and gravel and things like that in our drinking water systems. So that's kind of the relevance here, right? Is that this is a technology called groundwater infiltration. And basically what it does is we have an inlet into the system where we have water coming in to the ground, and we let it filter down basically through these different layers. And then we can collect the final water if we want to, or we can let it go all the way down to the bottom if we want to. But that's one way that we've kind of used what's already there in the soil as a treatment method. And this is for specifically wastewater treatment. And then we also want to think about protecting our wells as environmental engineers. So the vadose zone has that capillary fringe between the water table, and we don't necessarily want contaminants or microorganisms filtering down into the groundwater. So we want a thick vadose zone, and we want to protect this and make sure that this doesn't erode out, because this acts as a buffer between the well. We don't want microorganisms in our drinking water wells. That's a really bad thing. So that's why we care about that specific region. Then I just want to make a quick talk about different aquifers. So aquifers are going to be the saturated zone below the vadose zone. They're generally oligotrophic environments as well, and it's after that capillary fringe. And we can have many different types of aquifers. We can have shallow ones that are connected pretty closely to the surface water and that are going to have faster flow rates. We're going to have intermediate aquifers, which are normally confined, and they're normally within 300 meters of the surface soil. And then we can have really, really deep aquifers that are more than 300 meters below the surface soil. And they've got very, very slow flow rates. So when we talk about aquifers, the water is moving within the aquifer, but it's at different rates depending on the different depths. So this is just a picture that kind of shows that from a water resources standpoint, that we can have different types of aquifers. We can have things like confined aquifers. We can have intermediate, which are lower, deep aquifers, which are really, really deep, that shallow table aquifer. So this is just a figure to kind of show you where those lie. And then sometimes instead of the aquifer, we could have a wetland. So wetlands are in areas where we have swamps, bogs, and marshes, and they're normally characterized by temperate climates where the water table is really close to the surface. And we actually really love wetlands for wastewater treatment because they are really, really good at removing nutrients and other components. So we actually use them in wastewater treatment, and they've also actually been used for acid mine drainage. So they've been used as a remediation technique. And what we like about wetlands is that since that aquifer is a little bit closer to the surface, we're going to get both aerobic and anaerobic organisms, and we have a lot of vegetative matter in a wetland. So we're going to get continuous production and consumption, which leads to a more viable ecosystem. So this can translate itself into what we call constructed wetlands, which are a way of removing wastewater where we actually seed a specific bed with specific plants, and we let microorganisms actually grow because they're very beneficial to nutrient cycling. So this is a picture up at the top right of a constructed wetland, which is just one type of technology that's going to leverage how the natural soil environment works. So that's where we're going to stop on this particular lecture. We'll talk a little bit more about the different abiotic and biotic factors in the upcoming lectures.